Hello everyone, this is my introductory presentation on the Maple programming language. Unless otherwise shown in the presentation, all facts shown about Maple comes from this latest online guide from MapleSoft, the company behind Maple. Just a brief overview of Maple. First, it's originally conceived for symbolic computation at the University of Waterloo in the 1980s. Maple doesn't just refer to the programming language, but also to its interfaces such as a CLI, a code gen tool for producing code in foreign programming languages, and a worksheet interface for preparing interactive documents. The computation engine consists of a kernel and a math library that dynamically loads procedures and modules based on the code of the user so it remains performant. It is an imperative statement based dynamically typed language, although you can use optional type annotations in the procedures. Here are the features of Maple I found to be unique, as it is my first time encountering a math-leaning programming language that isn't a proof assistant. Number one, to display results. For most of the statements, they must end with a semicolon. Statements can be ended with a colon, but their results won't be displayed. But the computation still happens. This makes sense for a programming language where intermediate results are important, as though you're just given an algebra problem yourself where quote unquote showing your work is important, instead of say always invoking some print statement. Note the italicized for procedures. In this language, you can print procedures themselves. Number two, computation is done symbolically. Maple performs algebraic manipulations rather than going straight to numerical results. For full numerical results, there exist evaluation functions. Evaluation has two kinds, full evaluation and last name evaluation. There are two ways to terminate a statement, a semicolon if you want to see the results, or a colon if you don't want to see the results, but the computation still happens. As said, Maple computes and simplifies things symbolically. If you want something fully evaluated, you have to use evaluation functions. Maple is capable of doing calculus analytically, not just numerically. It doesn't just invoke numerical methods when you give it a calculus problem. It can also deal with ODEs, PDEs, linear algebra, and systems of equations, whether linear or nonlinear. Assignment is done using the colon equals. Note the result of a times 2 is an improper fraction, simplified as much as possible. If you want to see the typical fully computed value, you use eval_f, which is an evaluation function for floating points. As for display procedures, procedures can be displayed after their definition. Note the semicolon after the end proc. Maple also simplifies procedures and expressions in general. Note how the theta in the get angle procedure is now placed on the numerator because it is not enclosed with the sub-expression pi times. Maple simplifies expressions to some standard form. Maple has something called full evaluation. Full evaluation fully evaluates to the last assigned expression in a chain of assignments. In this case, C gets assigned to B gets assigned to A, then A is assigned to A. Oh, sorry, then 1 is assigned to A. So C shows a value of 1. If you want to display procedure definitions long after they've been defined, full evaluation doesn't work right away with a semicolon, as the procedure might be long and complicated. This behavior is called last name evaluation. To actually display the simplified procedure and its definition, one must use an evaluation function. Now we go straight into the the properties of the programming language as discussed in class. First is data types. Here are the data types in Maple. You have the typical primitives and their efficient representations. For example, integers can have different sizes based on the need of the user. And from these primitives, arrays can be constructed. There's also the complex data type. Integers have subtypes such as negatives, positives, even, odd, and prime numbers. As for simplicity and orthogonality, unfortunately, I couldn't find an extracted grammar for the language as it is closed source. I found a paper reducing Maple to its core calculus they named Mini Maple in an effort to mechanically verify it, but I'm not sure if that minimal language is representative of this actual one. A tutorial paper from 1986 mentioned that Maple's grammar is inspired from Algol 68, which oddly also doesn't exist in Zaitsev's Grammar Zoo project. Moving on, for expressivity, we have the familiar branching and looping constructs. For looping, there's the map expression for iterating in a functional style. There's also the zip function that merges two arrays by applying a binary function on each pair. Here are some branching examples. These are familiar to us at this point. Maple also has a ternary expression of sorts. In C, this is somewhat equivalent to this syntax with the question mark and the colon for separating the consequence of a Boolean expression. Looping constructs have many forms, as you can see on the left. There's also more there's also more famous while loop on the right. Maple also has a do until construct. Conveniently, it can also iterate through the alphabet with a feature for incrementing not only by one but by any integer specified. In this example on the right, the increment is by 2, so you see the output skipping every other letter. Those for loop increments don't need to be integers when not working with the alphabet. In this example on the left, we see an increment of 0.25. On the right, we see the map expression. As you can see, it takes a data structure, in this case, the one assigned to L, and is given a lambda x2x squared. That's why the result is L squared on every number. Here's an example of the zip function. If the two arrays don't have the same size, like in this example, as you notice, the first array has 6 items, the second array has 3 items. The one with the smaller size takes priority. The language won't assume default values if it went with the longer array, so it just chooses the shorter one. For abstraction, Maple has a concept of modules that bundle together related procedures in data. Publicly usable variables and procedures must explicitly be marked with export. Modules can be given a copyright. This is something new to me, but it makes sense given Maple's closed source nature. Another thing is that there exist special lifecycle procedures that get invoked whenever a module gets loaded or unloaded, providing avenue for running initializations or cleanup. Here are the examples of those lifecycle functions. In some sense, they are similar to constructors and destructors in object-oriented programming languages, but the difference is that these loading and unloading procedures have global effects. As modules are not classes, that is, modules don't have instances like classes do. For restricted aliasing, it's clear that Maple follows a call by value mechanism. Arguments are evaluated first before being bound to parameters, right before the statements inside the procedure get executed, possibly using those parameters. Exception handling is familiar. Custom errors can be thrown and caught in try-catch construct. In this example, if something bad happens during method A and the thrown error equals the string fail in all uppercase because this language is case sensitive, method B is tried instead. There are two ways to throw errors. Either you throw a simple string or throw a parameterized string with placeholders for the actual things to display. This is somewhat similar to C's printf's expected arguments. Errors can be sort of caught, even without explicit errors, with the finally clause as a kind of catch-all, similar to uh, the default in a switch statement in C. In this example, no specific error is caught if there's any, but at least the file gets closed if something happens wrong with the process contents of line procedure. For type checking, procedure parameters and variables can be given a type annotation with double colons. The double colon operator can also serve as a runtime type checking expression. Here is the examples of the usage of the double colon operator. To the left, type annotations, and to the right, runtime type checking. On the left, we see an error when you input a floating point for a parameter that expects an integer because the other function shown here expects an integer for a. Maple doesn't implicitly typecast arguments. In Maple, computation has two kinds: automatic simplification and evaluation. Simplification is not something controlled by the user, but evaluation can be controlled by the user after initial simplification is done by the engine. Remember that Maple simplifies expressions and procedures. That's what the simplification refers to here. Data structures are internally implemented using dynamic arrays. Here's an example of the dynamic array implementation of data structures used in Maple. Note that by data structures, we don't mean just the data structures you use as a programmer, but the internal representation that Maple uses. Say, for example, in this case, when representing rationals, or even representing the summation of expressions, as shown at the bottom here. So internally, it uses dynamic arrays for representing not just actual data structures, but also expressions in the language. Maple simplification feature goes deep theoretically. This algebraic simplification paper is mentioned in the tutorial paper. The core idea is a rewriting system based on something called the Knuth-Bendix completion algorithm. I won't pretend to know what this is in its entirety, but its purpose is to rewrite algebraic expressions into some canonical form. This algorithm powers Maple's simplification feature. In conclusion, Maple is a powerful symbolic computation programming language with a lightweight kernel, that is, the compiled binary is part of the language, and a breadth of libraries from many different domains in math, also written in Maple, so they are customizable and viewable by humans, and not something already compiled. And it has varied interfaces for different use cases. That's it for my presentation. Thank you. Here are my references.